Picture the largest snake alive today. An anaconda. 28 feet of muscle, 500 pounds of pure ambush predator. The kind of animal that makes wildlife documentarians nervous. It is, by any measure, a monster. Now double it. Now add 1,000 pounds. Now put it in a world so hot, so wet, so relentlessly alive that even that creature, that thing, wasn't the top of the food chain. It was just normal. That animal existed. It was real. And the closer scientists look at it, the weirder it gets. Not just in size, in everything. How it lived, what it tells us about our planet, and what its disappearance means for the world we live in right now. This is Titanoboa, and nothing about it is what you expect. It started, as so many great discoveries do, with someone holding something they couldn't explain. The year was 2009. A team of paleontologists was working a site in northern Colombia, a place called Cerrejón, one of the largest open-pit coal mines on Earth. For years, researchers had been quietly pulling extraordinary things from that rock. Ancient turtles, early crocodilians, plant fossils so perfectly preserved you could trace the veins in their leaves. But then one researcher lifted a chunk of rock, and embedded in it was a vertebra unlike anything in the collection. It was massive, dense, curved in a way that was deeply, unmistakably familiar, and yet completely wrong for anything they expected to find there. They ran comparisons: modern pythons, anacondas, ancient constrictors from other sites. The numbers kept coming back the same. If this vertebra belonged to a snake, and the geometry said it did, then that snake was somewhere between 13 and 15 meters long, possibly more. The team cross-checked. They brought in more specialists. They argued. They ran the scaling models again. The models didn't change. What they were holding was a piece of the largest snake ever to have lived on this planet. An animal so far beyond the limits of modern biology that its existence forced scientists to reconsider what limits even meant. They named it Titanoboa cerrejonensis, Titanic boa from Cerrejón. And the questions started immediately. Here's what strikes you when you actually sit with the data on Titanoboa. It's not just the size that's strange, it's that the size is the least strange thing. Start with the weight. Estimates put Titanoboa at somewhere between 900 and 1,100 kilograms. That's not a big snake. That's a small car. A creature that heavy on land would have its own organs pressing against each other under its own body mass. Breathing would be labored. Movement would be exhausting. Its heart would be working constantly just to push blood from one end to the other. So how did it function? The answer is water. Titanoboa wasn't a land predator in any meaningful sense. It was an aquatic ambush predator the way a crocodile is, except it was longer than a school bus and used the swamp itself as a pressure suit. Buoyed by water, its mass became manageable. Its muscles, kept permanently warm by the surrounding heat, stayed ready. It could hold position for hours without effort, just another log in a tannin-dark river, until it wasn't. But here's the part that genuinely unsettles biologists: the metabolism. Snakes are ectotherms. Their internal chemistry runs on borrowed heat. In a cool environment, a large snake is sluggish, inefficient, slowly starving. Modern pythons and anacondas are already pressing against the upper boundary of what today's tropics can support. They are, metabolically speaking, right at the edge. Titanoboa was nearly twice as long and more than twice as heavy as those animals. For that body to work, to hunt, to digest, to grow, the environment had to be doing something extraordinary. The Paleocene tropics of what is now Colombia were running at average year-round temperatures of at least 30 to 34 degrees Celsius. No seasons, no cool season, no relief, just permanent, wet, suffocating heat, month after month, for millions of years. Titanoboa didn't just live in that heat, it required it. Every degree of warmth was fuel. The hotter the world, the larger the snake the world could build. Which means Titanoboa isn't just a fossil. It's a thermometer. a biological record of just how extreme our planet has been, and could be again. To understand Titanoboa, you have to understand the Paleocene epoch, not just as a time period, as a sensory experience. It is roughly 60 million years ago. The dinosaurs have been gone for 5 or 6 million years. Earth is still processing that loss, ecosystems rebuilding, niches emptying and refilling, evolution running fast to fill the gaps. Mammals exist, but they are small, cautious, opportunistic. The real inheritors of the post-dinosaur world, at least in the tropics, are reptiles. And the tropics themselves are unlike anything alive today. There is no dry season at Cerrejón. Rain falls constantly. The canopy is so thick that the forest floor lives in permanent green twilight. Rivers overflow their banks and stay that way. The boundary between land and water is a suggestion, not a fact. And over all of it hangs a heat so total, so unrelenting, that it seeps into the rock itself. This is the world the Cerrejón fossil site preserves in extraordinary detail. Not just Titanoboa, everything. Giant turtles with shells wide enough to use as a dining table. Crocodilians with blunt, crushing teeth designed for something armored and slow. Fish in abundance. Dense layers of leaf litter compressed into coal. It was a complete ecosystem. And it was an ecosystem designed, almost accidentally, for one animal to become enormous. Titanoboa sat at the top of that world. Not because it was fast, not because it was aggressive, but because it was patient in a way that smaller animals couldn't afford to be. A snake that size can go weeks between meals. A single large turtle or crocodilian provided enough calories to sustain it for a month. It didn't need to hunt constantly. It needed to hunt correctly. Once. And in that swampy labyrinth, correctness meant stillness. Titanoboa would lie motionless in shallow water, its body temperature stabilized by the swamp around it, its outline broken by roots and vegetation. It could feel vibrations through the water. It could sense heat. And when something came close enough, the strike was less a movement than a fact. An event that had already happened before the prey understood what was occurring. The constriction pressure scientists estimate for Titanoboa exceeds 400 psi. That number is almost meaningless without context. So consider this. At that pressure, the bones of a large crocodile not bend, not crack, shatter. So why isn't Titanoboa still here? The simple answer is climate. But the simple answer is also the terrifying one. Roughly 56 million years ago, Earth began a slow but irreversible cooling trend. Global temperatures dropped. The Paleocene gave way to the Eocene, and the relentless heat that had made Titanoboa possible began to ease. Just a few degrees, that's all. But for a cold-blooded animal whose entire biology was calibrated to a specific thermal environment, a few degrees was everything. A cooler world meant a slower metabolism. A slower metabolism meant slower digestion. Slower digestion meant less energy available for growth and movement. And for an animal requiring thousands of calories just to maintain its body mass, the maths turned brutal very quickly. It wasn't sudden. Titanoboa didn't die in a catastrophe. It shrank. Generation by generation, the largest individuals were the least viable. They needed the most heat, the most food, the most of a world that was gradually withdrawing. Smaller individuals survived longer, but the ecosystem was changing too. The giant turtles became rarer. The swamp forests dried at their edges. The food web that had sustained a 15-meter ambush, predator began to lose its lower rungs. Titanoboa didn't go extinct because something killed it. It went extinct because the precise, narrow set of conditions that made it possible simply stopped existing. And that is the part that should stay with you. This animal, the largest snake in Earth's history, a creature that reshaped our understanding of what biology can produce, was dependent on a world running just a few degrees warmer than ours. Not dramatically warmer, not science fiction, warmer. A few degrees. That's the margin between Titanoboa existing and Titanoboa being impossible. We are, right now, in the middle of raising global temperatures, slowly, incrementally, by a few degrees, scientists are not predicting Titanoboa's return. Modern ecosystems don't have the Paleocene food webs that supported it. The giant turtles are gone. The swamp forests are fragmented. But what the fossil record of Cerrejón tells us, in unambiguous biological terms, is that temperature is not just a background condition. It is a dial. Turn it up, and the upper limit of what life can be rises with it. Turn it down, and things that should not be able to disappear do. Titanoboa is proof of both. There is a vertebra in a museum in Washington, D.C. It is roughly the size of a human fist, slightly curved, worn smooth by 60 million years of pressure. If you didn't know what you were looking at, you might not give it a second glance. But that bone contains multitudes. It contains a world so hot it seems impossible. A predator so large it redrew the limits of biology. An extinction so quiet and gradual it looked, from the inside, like nothing at all. And it contains a question that every climate scientist working today already knows the answer to, but that the rest of us are only beginning to understand. The planet has a temperature, and life is built around it. Change the temperature, and you change what life is possible. Titanoboa lived that truth, and then, when the world moved on without it, it became the proof.